In the early 2000s, nuclear power was in trouble. Public trust was gone. Costs were rising. Construction times were getting longer, not shorter. Many believed the nuclear age was coming to an end. Then Westinghouse said something bold. What if the problem wasn't nuclear power itself, but how we were designing reactors? This is the story of the AP1000. The AP1000 was created in a world shaped by accidents. 3 Mile Island showed how small failures could escalate. Chernobyl showed what happens when design and culture fail together. From that point on, nuclear engineering had one central goal: safety. But instead of adding more systems, more pumps, and more complexity, AP1000 chose a different path. It chose simplicity. The AP1000 is a Generation 3 Plus pressurized water reactor. At first glance, it looks familiar, but inside, its philosophy is completely different. Traditional reactors rely heavily on active systems: electric pumps, diesel generators, and constant operator action. AP1000 asked a simple question: what happens if everything fails? Its answer was passive safety. Passive safety systems do not need external power. They do not need human intervention. They rely on gravity, natural circulation, and basic physical laws. If the plant loses all electrical power, the AP1000 does not fight the situation. It lets physics take control. Water flows downward by gravity. Heat rises naturally. Pressure differences move coolant without pumps. One of the key elements is the in-containment refueling water storage tank. Instead of being far away, emergency cooling water is placed inside the containment itself. When needed, it simply drains into the reactor vessel. Another critical feature is the passive containment cooling system. Water stored at the top of the containment flows down its outer surface, removing heat without fans, motors, or electricity. For at least 72 hours, the reactor can remain safe with no operator action at all. On paper, this was revolutionary. Fewer components meant fewer failure points. Fewer systems meant lower maintenance, and simpler designs promised faster construction. But reality had other plans. AP1000 was not just a new reactor. It was also a new way of building nuclear plants. Westinghouse pushed for modular construction. Large sections of the plant would be built in factories, then shipped and assembled on site like industrial Lego blocks. In theory, this would save time and money. In practice, it created chaos. Modules arrived late, unfinished, or out of tolerance. Design changes continued even after construction had started. Supply chains were unprepared for nuclear-level precision. Costs exploded. Schedules collapsed. In 2017, Westinghouse filed for bankruptcy. 2 AP1000 projects in the United States were affected. Vogtle in Georgia survived. VC Summer in South Carolina did not. Many declared the AP1000 a failure, but the reactor itself had never failed. In 2023, Vogtle Unit 3 finally entered commercial operation. It became the first new nuclear reactor built in the United States in over 30 years. It worked. The passive systems performed exactly as designed. The reactor was stable, predictable, and safe. Vogtle Unit 4 followed. The lesson was clear. The AP1000 did not fail as a nuclear reactor. It failed as a construction and project management experiment. The technology was sound, the execution was not. So what does the AP1000 really represent? It is not the future of nuclear power. Small modular reactors and advanced designs are now taking that role. But the AP1000 proved something essential. Nuclear power can be made safer, not by adding complexity, but by removing it. This was Reactor Atlas. One reactor, one story, one truth.